All right. So I don't know, Anthony. I saw you come on first. I don't know if it matters, but let me just say the easiest way for me to keep track of it is to have you guys shoot the question on the chat. But Anthony, since I
Okay.
just saw you first, I'll take you first. So go ahead. What do you got for me?
Um, I actually have a question about the lab
Oh, okay,
for
good.
122.
Yeah,
So I have a I have two graphs for the stuff that I need to turn in. I just need clarification on what I actually need to turn in.
Okay, fair enough. Yeah. Um, the let me think about that one. And this one was on the capacitors,
Yeah.
and you should have two graphs. Um, and so definitely those two graphs. One, it
Yeah.
should be plotting capacitance versus distance for step 6,
Yeah.
and capacitance versus area for step 7.
Versus like so there's the capacitance versus the distance that you're sliding the plate off. And then
Yeah.
there's the capacitance versus the plate being lifted up.
Okay. Right. So
Right.
step
Okay.
6 is step 6 is being lifted up.
Yeah. Okay.
So that's the one you want to plot because that's what's in that equation on distance.
Okay. I actually I put three graphs here with some other thing, but I have the two important ones there anyway.
Okay, yeah. So
Okay.
the one that you said about the distance you slide it, don't plot that one.
Oh, don't plot that one.
Yeah, don't plot that one. That one should the only reason we did the distance was to change the area because we wanted to see how the capacitance changed with area.
Right.
Okay, so that's what you want to plot, capacitance versus area.
Capacitance versus area. Okay. Okay.
Yeah.
Okay. So I do have to change that because I have it the capacitance versus the distance slid.
No, yeah, okay, fair enough. And I understand that's a pretty involved class or lab there, but the idea was to show you that the two factors, uh, and area being one of them, is that the capacitance would change with area.
Okay. Okay.
So, anyways, that's I guess part of your answer. Those two graphs. The other one, let's see. Uh, you're just going to have a sheet of paper and write down uh, basically what I wrote on the board in the video. That was okay. First of all, what's the like step 1? What's the capacitance of those? And then I think you were asked to do a percentage of how close was the number we measured compared to what it said on the side of the capacitor.
Okay.
I might even have done that calculation. I'm trying to remember now. I remember saying on the video at first I wasn't going to do it, and then I think I did it.
Mm-hmm.
Okay. And then step 2, again, you're just to essentially write down what I kind of did in there was I hooked the two, and I think that one they were in series. So you were supposed to write down what the capacitance was when you measured them in series, and then your calculation. And
Yeah.
I think that's the one that I said, okay, I
Right.
won't do that calculation. I'll let you see if you get something close. And then I actually ended up doing it because I wanted to show you guys I think a real advantage is using that inverse key on the calculator.
Mm-hmm.
And then step 3, because this was a long lab. Step 3 was the same idea as step 2, but they were in parallel.
Yeah. Yeah. I think I have everything except I need to fix those because I graphed the wrong x-axis.
Yeah, yeah. And another quick thing is at the end of it, there's I believe 2 questions, but one of the questions that I know I've got a lot of emails on was the one that does the capacitance change depending on how much voltage you apply to it.
Yeah.
And the answer is supposed to be no, it does not. Hopefully you saw that the capacitance was geometric factors like
Yeah.
area and distance, right?
Right.
Okay,
Okay.
good. Good. Nice.
All right.
All right. Oh, okay. Good. Andrea, let's see, problem 18, chapter 5. Okay, so let me, 18, chapter 5. Let me find that one here. Chapter 5. Let me scroll down. Number 18. This is a good one. Let me write a couple things before I share my camera screen here. This one says Mars has a radius. So let me just put here Mars and some information about Mars. Mars has a radius of 53% of the Earth. That'll be kind of a rough number there, okay? And has a mass of only 11% of the Earth. So let me write down radius, let me write down mass, and then the question is estimate the acceleration of gravity. All right, so let's see, let me come back here.
In case you wanted to make a note of it, Mike, I started a timer when you started recording, so this problem is about at 5 minutes 30 seconds.
About 5:30, thank you.
Yeah.
That would be good to get a timer here. Bummer, the only timer I have is my phone. And I'm using that for, thank you. I do want to make a note of that. Okay, so I'll put that on my note and I'll also write down problem 18, chapter 5. That helps with it. Okay, nice. Okay, and so then let me go to share screen. Be nice. Okay, click share screen. There we go. And okay, there's the iPhone share. And then, good, here it comes. Let me screen sharing. Okay, hang on. How come? Usually it just pops right up and lets me select Zoom on my phone. It's hunting and finding nothing. Oh no. I did anything different? I don't think so. Not good. It's not finding my computer this time. Let's see. Do I give it more time or do I do a workaround here? Huh. Crazy. Yeah, I really want to get this working, but I might do a quicker workaround. Apologize, guys. My phone doesn't want to connect. I'm going to try. What if I do this for a moment? If I go to the whiteboard. All right. Did the whiteboard share? Yeah?
Yep.
Yeah.
Okay. Well, I'm going to go to the whiteboard at least for this one. I'm going to let this spin for a while. Okay, so, looks like I got a mess here on the whiteboard from another question. Let me see if I can get my eraser going. Eraser, clear canvas. Oh, nice. Okay, so I'll try not to make it too messy here. Let's see if I can get my left hand around here to write a little better. But the force of gravity is what this chapter is all about. And Newton's universal law of gravity says this. Okay? And so the idea of this problem is, of course, use this, which is from chapter 5, the universal law of gravity, but also from the previous chapter, which is acceleration is force divided by mass. So if we put these two equations together, we can say that the acceleration is, and then we would have g, and I'm kind of hoping you see here that if you let, say, M2 represent, say, the planet of Mars, and M1 representing whatever object you have on Mars, when you go to calculate the acceleration, you're dividing by the mass of the object. So putting these two equations together would look like this, an M1, M2 over R squared, and then you would be dividing it by M1. So the mass of the object would cancel off, and you would have the universal gravitational constant, you would have mass of the planet Mars, and you would then be divided by R squared. So that would be I'd call the first part of this problem, is just realizing that to get the acceleration on another planet, or any planet for that matter, you would take the gravitational constants, you would take the mass of that planet, and you would divide it by the radius of that planet squared. So in this case, you now have two options, especially since you're working remotely. There's always good and bad about this remote situation. And maybe this is the good one, is you could just ask Siri or Google and go, hey, what is the mass of Mars? And then just put in the mass of Mars. And you could also ask, what's the radius of Mars, and put it in. But based upon how the problem was given, they want you to say that it's 53% of the Earth's, excuse me. It's 53%, no, a mass on top. Try that again. It's supposed to be a decimal point. It's 11% of the Earth's mass. And downstairs would then be 53% of the Earth's radius. And of course, that whole quantity squared. So like I said, working online probably would be easier just to look up the mass of Mars and the radius of Mars. But using the information from the problem, there is something kind of neat to see, and that would be this next step. If you change colors here, think about what's in my equation right now and realize that this factor of 2 right there on the square can be distributed here and here. And then if you group this G with the radius, I mean, the mass of the Earth, and with the radius squared, those would look like that equation, but for the Earth. And so what I mean by that is you would still be left with this 0.11 on the top, and you would still be left with the 0.53 squared on the bottom, but the other three factors would give you the acceleration on Earth of 9.8. And so I think that was the intent that the author was trying to get you to do, not to necessarily look up the mass of the Earth or the, the mass of Mars or the radius of Mars, but you can do that. So with that in mind, I can now grab my calculator and just look at my phone here. Yeah, see, it's not connecting that way. I want to see if I can maybe do a different connection. All right, but I'm going to take the 0.11 and divide it by the 0.53 squared. And so I'll write this on the whiteboard in 2 steps. This will be a 0.39 times the 9.8. And so times 9.8 on my calculator gives me an acceleration of 3 points. It looks like it's about 8.4. And I didn't put in my units way back here, meters per second squared. Let me do that now, meters per second squared. So that's what they were after. But hopefully that helps. Okay, so I'll stop sharing that. And Andrea, did that help? Are you still around?
Yes, thank you.
Okay. Good. All right. So then, let me write down the next one here. So the other one is also 102. That's number 39. So problem 39, chapter 5. Okay. Let's see if I can grab that one. And my phone here is going to disappoint me. You know what I could do? Well, I'm going to answer this one since it's a 102, but I wonder if I should log in by Zoom on my phone, see how that does instead of try to hook my phone to the computer. But I'll try that next. Okay, did I see that right? Yeah. Oh, conceptual question. Good point. This is a conceptual question. Okay, so Daniel, 102, conceptual question 39. Okay, let me just jump back over here to the questions. 39, it says, when the tide is high along the American western seaboard, is the tide in Japan a high tide or a low tide? And keep in mind that Japan is approximately 90 degrees west of San Francisco. So that important piece was that it's a quarter around the world. So let me draw a picture for you. I think that will help. Let me come back to the Zoom. Let me share this screen, and I'll go to my whiteboard here and say, all right. So let me kind of move this up here. And here's the idea that if you had the Earth, and so here's kind of this Earth, the best circle I can draw here on my computer screen. Okay. when either the sun or the moon, or they actually both are working at the same time, so I'll just for simplicity have them work together. So here's the sun, and say maybe here's the moon. Both of those are pulling the water. And so I'm going to make a little bulge for the water. I know one thing that could be a little nicer here on the screen is I could actually do colors. So maybe I'll go to blue here for the water. But the idea that you've got hopefully out of the tides is that the water would bulge up being pulled towards those planets. The one that's not so obvious is that the water would actually bulge opposite of it. And it's not because it's pushed away, it's actually because the Earth is pulled away from the water. And so if you, I don't know, maybe I'll make it orange here. This area in orange gets pulled the most. And that's why it gets closest towards the moon. This area in green, which is the Earth, gets pulled the second most. So that's why the orange gets pulled a little bit closer to the moon and the sun than the green. That's why it makes a little bulge. It gets pulled away or towards them more. But another one that's not quite so obvious, which I'll do in red, is this water over here is still pulled towards the moon, but it's not pulled towards the moon as much as the green Earth is. And so because of that, there is a bulge on the backside. And you got to remember then that the Earth is then rotating or spinning around, making a circle, something like this. So because of that, in a given day, as we sit on the Earth and make one revolution, we will then move to, say, this part here, which would be in a bulge. So we would say that's high tide. And then about a quarter of the day later, so 6 hours later, we would be in this part of the Earth. No, excuse me, not that we moved on any part of the Earth, but the Earth moved into a different part of the bulge of the water. And that would be where the water is low. It's been pulled away, that because the water had to come from somewhere. And so these bulges account for the high tides. And so this is the low tide. So 6 hours later, we would have a low tide. Then over here, 6 hours later, we'd have a high tide. And then over here, 6 hours later, we would have a low tide. So that's how the tides work. Now, specifically then for this question is then saying, let's say you are 90 degrees apart. One place would be at a high tide and one place would be at a low tide. And now I need to go back to the question. I forget which one. Was it San Francisco or Japan? It says, when the tide is high on the American West Seaboard. So when it's high tide in, say, San Francisco, it would have to be then low tide in Japan. That's what the idea there was. So,
Oh, okay, thank you.
good. All right, and this will be a little bit of a pain, but I'll stop sharing that and come back to I can see the questions here. All right. Oops. Mine was exercise 18. Okay, that's fine. I guess I did the wrong one. All right, so let me go to, and I got to be careful with that. Yeah, I forget that the 102 they have numbered in problems and in exercises. All right, so let me try it again. Sorry. Let me come back to the questions here on my screen here. I just saw 18. Oh, now wait, I'm a little confused here. Number 18 exercise is the Mars and Earth acceleration. Conceptual 18 says if you're standing on a bathroom scale in an elevator and suddenly the cable breaks and the elevator falls freely. I'll tell you what, let me change my notes here. I'm going to say, okay, so I did the exercise before. Now I'm going to do the conceptual. And so let me do this bathroom scale one. It says you're standing on a bathroom scale in an elevator when suddenly the cable breaks and the elevator begins to fall. How does the reading on the scale change just before and just after the cable breaks? And how does the force of gravity on the that the Earth exerts on you change over this same interval? Oh, great question also. And again, I'm going to, I think I can still use this on the whiteboard. I won't worry about my phone. I'm going to try to answer this one. In fact, I'm going to come back up here. Maybe I should even just label this number 18, and this is the exercises. Whereas here, this was number 39. This is the conceptual. Because now let me try number 18, conceptual. And let me help you with this picture here. If you were standing, and it doesn't matter if you're in an elevator or just in a bathroom on a scale, if this is you, and I'll make it a big scale. Here's the scale, okay? And you did this free body diagram, then you would do something like this. Let me just make a little circle here for representing you. You would be pulled down here by gravity. So that's your weight. Gravity's pulling you down. And what's pushing you up is this contact. We'd call this a normal force with the scale. But this would be the reading on the scale. This is what a scale does. A scale reads really how much it's pushing up. And so for a scale to work correctly, you want your net force to be zero. So you want to be standing on the scale and not moving, because it's when these two forces here are equal and opposite, you get a net force of zero. So keep in mind that the scale does not read the net force. And surprisingly, a scale doesn't really read gravity. It reads what is pushing up. And the key to using a scale correctly is to make sure that the pushing up is the same as gravity pushing down, giving you a net force of zero. So to use a scale correctly, you must stand on it and stationary. And normally that's what you would do. You would get on the scale and you would hold still, and the bathroom wouldn't be moving. And so the pushing up, and I'll circle in red right there. So the normal force would be the same, circling green.
But are you sharing your screen? Because it's not showing up on my Zoom.
Oh, thank you for saying that. I might have switched over too quickly. I did. Share screen, whiteboard, bummer. All right. Can you see it now?
Yeah, I can see it now. I wasn't the one with the question. I just joined and I was say something. But yeah.
Yeah. Okay. Let me shrink it up a little bit. I apologize. And so to summarize what I was trying to say with this screen, and I'll highlight number 18 here, right here. Right there. Okay. And I'll just start again here, but to make it understandable, to understand how a scale works is crucial here. So I'll say it again, this picture right here, I'll circle in red. with somebody standing on the scale, the upward force right here is coming from the scale. That's the normal force. Must be equal to the downward force for the net force to be 0. And so to use a scale in a normal fashion, okay, normal fashion, this net force would need to be 0. That way, the reading on the scale, the red one here, this one here, check in red, and this one here, check in green, are equal to each other. But what this is suggesting is that you are not using the scale in a bathroom. So let me keep drawing here. I'll move that up a little bit. And I'm going to redo the free body diagram. And I'm going to just make a little dot to represent this person here. Well, what's going to happen is when the cable breaks, you will still be having this force of gravity. That doesn't change. What does change is as you fall, the elevator falls, and the scale that's between you and the elevator floor fall. So there is no force pushing you up. That's the whole reason you go down. Sadly, sometimes when people are skydiving, they'll say, oh, I am weightless. And that's not really a good way to describe it because you're not weightless. The weight is pulling you down. What you don't have is this right here, the normal. You don't have an upward push that we're used to. We're used to the ground pushing you up. And so the whole thrill of skydiving, I get that. There is a dramatic change. There's no upward force from the ground anymore. And so that's a very much of a change. So things feel very, very different. That's why, we like things like roller coasters and skydiving, and it just feels different than what we're normally used to. But it doesn't turn off gravity. It turns off this normal force. In fact, that's why you would have a net force now that is not 0. So I'll put here net force does not equal 0. See, so if your net force is not equal to 0, then of course you accelerate, and that's why you go down. So this was a long way to get to the final answer. The final answer really is that the normal force would, before the cable breaks, be equal to your weight, and then after the cable breaks, would be equal to 0. Whereas gravity is always equal to your weight, whether before or after the cable break. That doesn't change gravity. What changes is that normal force that all held. And so I can see you guys again. I'll stop sharing. And don't let me forget now to turn the sharing back on when I jump away from this. So did that help? I forgot now who asked that. Andrea. Okay. Okay, well, I'm going to move on. Who was next here? Alicia, that it? I also have a
Yes.
Physics 122 question. All right.
Yeah, I have a question on the lab. So it asks in one of the questions what the let me get that up. The let's see. The accepted value for the dielectric constant of plastic, but like depending on which plastic
Thank
you're
you.
talking
Yeah.
about, they're really
Uh,
different. And I didn't
I-
really find anyone close to what we measured. So I kind of just
What-
wondered what I should use for that.
What did we measure?
I think our measurement was 3.69.
Yeah.
Yeah.
Yeah. Okay, that's what kind of what I remember. Okay, and then that's normal. Now,
So it
so
looks like the book has a polystyrene.
yeah, and that's not what we have.
Yeah.
I apologize for this. I should have said something. I get this question all the time in a face-to-face setting about towards the end of the lab, and I go, oh shoot. And I usually just tell students, we can't answer that well because I'm not sure what kind of plastic we have. I
Okay.
think it's nylon, but it's
Okay.
definitely not a polystyrene. What are the and ones in the book I list polystyrene and there's
Let's
another
see, they've got right, let me go.
Well, so I again I apologize. I know the book does not list what we have.
Okay, I mean they have nylon at it looks like 3.4.
Oh, good. And you got 3.6, or we got 3.6 since I'm your lab
We got,
partner?
I think 3.69. Yeah.
Yeah. Okay.
So
I'm
I'll
pretty-
just go with the value for nylon. Okay.
Yeah, go with the value for nylon. And I again apologize. I should have remembered to put that in the video. That is a normal question every time I do the lab because it asks that question and there's so many different kinds of plastic and we don't even know what kind of plastic we have anymore. We keep changing it. We just go, well, this will be fun. This will work.
Okay. And then it looks like discussion question 3 is basically a repeat of, I mean, I already wrote those steps in like 3, 4, 5,
Yeah.
basically, but it's like asking for them again. I mean, I guess I can just cut and paste.
No, don't. I've never figured this out. This comes up every year also. The author, for whatever reason, in the discussion questions, asks the same thing they've already asked, and
Yeah.
I've never quite got that. And I tell the students, when you come across that, and you will come across it a lot more, you can just write
See above.
Step 3, or step
Okay.
4. See above is fine too.
Yeah.
I don't want to make more busy work for you. It is. If you recognize that you already answered it, that means you know the answer, and that's good.
Yeah.
That's
All
the
right.
goal.
Those were my questions on the lab. I might have some, I'm doing the homework now. But I think I'm good for now. Thank you.
All right. Yeah. Good. Thank you for that question. The lab. Yeah. The lab manual sometimes is less than perfect, but I really like doing the big concept is good, like measuring the dielectric constants. All right. On to, let's see, next year, Andrew. What specifically are we turning in for the lab? I think I answered that for you, Andrew. Are you still here? You're gone. Okay, I'm going to go with the idea that I grabbed you and you were probably typing that question, and because we answered that one. Okay. Daniel, what is the best way to study for the test on the 29th? Oh, how about a couple answers to that? Number one, practice problems. Now, obviously, you're doing the homework, and I hope this makes sense, but I like to describe the homework problems this way. If they're taking you a long time, this is a self-correcting mechanism. Work on them because you will end up studying a long time because they're taking you a long time. If you fully understand the material, they only take you a short time. And so what I like to say is, okay, if you want to get ready for the test, go ahead, and presumably you've already done all the homework. Grab another problem in the book, one that I didn't assign as a homework, and pick it at random. And say, okay, I'm going to do this problem. And do that with a couple of problems. And if you can knock those out really quick, number one, it won't take you very long. But number two, that will tell you you really know the material and you're ready then for the exam. If they take you a long time, that's a sign that you really need more practice. And the taking the long time is giving you that more practice. And I like to describe it that way better than describing it with time, because it's just a matter of, are you ready or not? It's not a matter of how much time did it take, you know? So I guess it would be a little bit, if I can do an analogy to maybe a professional runner trying to qualify for the Boston Marathon. You know, they know they're ready for something as hard as the Boston Marathon when they can run another marathon of equal difficulty in under 3 hours, which is why they won't even, let you run the Boston Marathon in the race group. Anyways, you can always do it as a fundraise thing, but you can't even get until you get under 3. You're not even allowed to be part of it. You're just not there. You're not ready yet. And for some people, they can train for 6 months, maybe as little as a year, or and say, okay, I'm ready for the Boston Marathon. Other people, this takes years and years to build up, and so it's not a way of how much training should I do to get ready for the Boston Marathon. It's more of, okay, how do I know when I'm ready for the Boston Marathon? Anyways, so that's my first answer. This is how you'll really know if you're completely ready for the test. That you could grab one of these problems at the end of the chapter. You could do it in under 25 minutes.
Okay.
Okay. So let me say that's answer number one. Now, answer number two is, and you'll see this on Sunday. On Sunday, I'm going to put out the next week's material. What are we approaching? Week 5? And so as we approach here week 5, and as we get ready for the exams, and I say exams because the 102 has an exam coming up a little earlier than you guys. Yours is coming up on the, 29th, I believe?
Mm-hmm.
29th is what it says in Canvas. So
Yeah.
that's what I'm going off.
Yeah. And that's what I'm remembering. So I'm going to give you a little bit of insight on that on Sunday. And one of the things I'm going to say here is I've got a nice review of the chapters. I call it a test review. I did this review. Well, I can't remember. They're not as old as the video lectures you're watching. I think the video lectures date back to when I did them in 2013, and students just appreciated the video lecture, so I always left them. And I had no idea the pandemic was coming up, and now I'm using those as a replacement of the lecture, as you know. But then I started doing a Saturday, or no, I think they were Sundays. It doesn't really matter what day, but on Sundays I started doing a 4-hour review. What I did is I grabbed some older problems from tests, and I just came to campus. I think it was like a 1 o'clock on a Sunday, so 1 to 4, and just went over it with the students, and the students were there live. But I also video recorded it. Anyway, so I'm gonna send that to you, and that will give you not only more practice, but I'll also shoot the questions to you. Okay, and so I'll shoot the questions, and I'll even encourage you to say, try the questions that I'm sending to you. Try those first before you watch my review, and before I show you how to do them. You try them first. That'll give you an idea of where you are. And
Okay.
It'll also give you an idea of the type of problems that will be on the test. And hopefully that will alleviate nervousness, because I know when you get nervous on a test, you do even worse, and you want to make sure that, you do at least as well as you've studied for, not worse because you're nervous. But seeing those really helps. And so I'll send them to you in PDF form, and then I'll send you the video of me working them out.
Okay, so we could check our answers later.
Yeah, and then
Was
also
it-
I'm going to give this on Sundays, is that if you look ahead in the video lectures, okay, before I start the next chapter, chapter 17, the students that semester took the exam, and I believe I went over the exam in class. So you will
You did.
actually see that exam and me go over them. And so I want to make sure everybody understands that. Some people probably already caught that. I think that was Laura chiming in saying, I think was that you saying you saw them already?
I've been looking at a lot of stuff, so yeah, I think that was one of them.
Yeah. So if you look ahead, you'll see that. But I want to make sure that I give everybody a fair chance and give them a chance to look ahead. But so you will see the 5 questions on that test, and I believe that was on 2013. And then the problems I put together came off of multiple tests, and I think it's the equivalent of 2 tests if I remember right. Anyways, so with all that, you'll actually see this next week 3 of my old exams and really get a good idea of the problems and the difficulty, and I'll go through them all, and that will be a help.
Okay, cool.
And also, keep in mind this, I deliberately, just because this new online stuff is new to me, new to you, but notice that the test coming up is chapters 23, 24, 25, and 26. And you just did 26 this week, or if you're not behind, you did. I mean, this has been such hard material, you may be behind. But the test is not until the 29th. So you still have 11 days with all this now to sink in. And so I know we've been rushing. I know it's been a lot, and I know you've probably been feeling a little overwhelmed with it. But remember now, no new material for the next 11 days as it sinks in getting ready for the test. Although I will say, if you have the time, and you, it would be helpful if you started chapter 27. But if you're still struggling to learn the material, don't start 27. You can pick that up later, and you'll see 27 is by far the easiest chapter we've
Had so far.
Yeah. I mean, definitely 27 is the easiest. I think 27 is the easiest for the semester. So you've seen some hard chapters for the semester, and now you're about to see an easy chapter. And well, I shouldn't say it easy. I don't think any of them are easy. I should say the easiest. How's that?
How much time will we have for the test?
So I'm going to go with 2.5 hours. In a normal face-to-face setting, it's 2 hours. But I'm going to give a little time for you to scan and upload, and then and presumably that won't take you a half hour. Another thing that so you'll get a little more than a normal class setting. I will also what am I trying to say here? Kind of let you pick your 2.5 hour window within that morning time. And I'll also then throw out there that if anybody can't schedule it in that morning time, I get that, and I'll work around that. But the default will be in the morning of the 29th, which would have normally in a face-to-face setting would have been the first lecture and then the second lecture. So that would have been from 8 a.m. to 12:30. So from 8 a.m. to 12:30, you pick your 2.5 hour window, and then we'll all get that test done in the morning. And there'll probably be a few exceptions because it's I already promised a few people that because of the way we're learning, it's just different, and try to make things like they have a job at that time, and some are valet parking at that time. So
There was also one question I forgot to ask you on the lab. So for, I think it was 7, where we're filling in that chart, you only went up to 50 millimeters, but their thing goes up to 75, right? I didn't like miss. Yeah. Okay. So we're good on
Yeah.
that.
No, yeah, you didn't miss anything. It would
Okay.
tip over.
I was like, did I just space out for the last 5?
No, great.
Okay.
You're asking the same questions that I normally get when I'm just sitting there in lab. They soon go, wait a minute, the chart goes further. And I go, yeah, you just go as far as you can until it tips over is what I tell them.
Got you. Cool. All right. Thanks.
Yeah. Let me actually write that down. I'm going to say, what was that? Questions?
7, I think, on the lab.
Well, but I'm going to just go questions about test. How about that? Just about exam 1. But hopefully you, and I bet about it, other people have, besides you, Daniel, questions about that test. And I'm going to try to address that with the long description this Sunday coming out. All
Cool.
right.
I was just trying to like plan my next week ahead so that I can keep track of everything.
Yeah. Okay.
So thanks.
Okay. All right. Let me come back here to the chat room. What is the best way to study for the exam? Okay, that was you. And then a thank you. Oh, you are welcome. Could you please do chapter 26? Ah, yes. So chapter 26, number 11. And now I'm really going to miss my screen share. So I'm gonna give me a second here. I'm gonna try something here. My crazy screen here. Let's see if I can, since I can't seem to get it to work with this connecting.
Are the 26 chapter 26 questions basically like Ohm's law with volts, amps, and resistors, just with capacitors?
Yeah. Okay. Give me a second here, though. I just sent you guys the Zoom link. Aha, here it is. So if I get that, never tried to join Zoom on my phone. But I know you can. That didn't work well. Let me try that again. Zoom meeting. This looks like it. Okay. What if I just tap it? Ah, then it says join meeting. Good. Okay. Join with video. Yeah, let's do that. Oh, okay, okay.
This meeting is being recorded.
Okay. Oh, I get some terrible feedback.
If you mute the phone, it will take away that feedback.
Yeah, okay. And then let me also turn the volume down. That's because that's getting then picked up on my laptop. Ah, that should do it. Okay, then, oh, I got to mount my phone upside down. I think I can do that. Ooh, and it turned it a little bit. Oh, okay, okay. I see. All right, let me Try something. Oh, but then that's not going to get very big. That's going to be a problem. Hang on. Let me twist my body this way. Okay. Now, let me unmount it and see. Aha. Okay, now if you're on your phone, and I can, oh, it says only the host can share. I think I can change that. Okay, participants share, okay. Nice, okay, let me see if I can share this now. Share. Screen photo, I guess I want screen. Share, so what? So if I do share screen, how come when it shares, what do you guys see?
Screen broadcast.
Yeah, that's what, okay.
But that's like all we share or all we see.
Yeah, I wonder, let me turn that off. I was hoping this would be easy. I could just share my screen and it would go to the camera on the phone, but it doesn't do that. I guess the phone app's a little different. Okay, I might go back to my whiteboard there. Yeah, let me do this and I'll play with it on the break, I guess. That's really a bummer. It won't connect. I was really liking the way it was connecting and making things kind of nice. Well, let me try. It looks like there's different windows I can go to. Oh, those are just all you guys. That's pictures of you guys in the room. All right. Well, I'm going to leave the meeting on my phone here for a second. All right. Well, that's really bumming me out. Okay, so I'm gonna try to answer this question. I forget who asked it. Andrew, huh? Could you do chapter 26, number 11? And yes, I will here. I just don't have my camera working. And so let me jump over to your guys' question. Let's see. So let's leave the 102 for a moment. And okay, here's, I found the homework for you guys. Let's see if I can load it up. All right, chapter 23. There we go. Chapter 20. What number is this? 25. Okay. Keep going. You said 26, number 11. Okay, 26, number 11 says an air-filled spherical capacitor is constructed with an inner and outer radius of 7 and 14 respectively. Calculate the capacitance of this device. Okay. And let me just write down the number 7 and 14. So I can remember that when I come back here. And then part A says, what is the capacitance? And then B says, what is the potential difference between the spheres result in a charge of 4 microcoulombs on the capacitor. So we're looking for the voltage. We would need to know the capacitance. All right. So with that in mind, let me come back to the Zoom session here, and let me not forget to share my screen this time, like I did last time. All right. So share. Let's go to the whiteboard here. Okay. So maybe I should ask, am I doing this right? Did I share my whiteboard?
Yes.
Okay.
Yes.
Thank you. Okay, so let me scroll up here and write, what did I say this was? Chapter 26, number 11. Okay, so the first part of this says, A, what is the capacitance? Question mark. And so this will be a nice chance to review what capacitance is. Capacitance is a measurement of how much charge would you get, and I should say magnitude of charge, for a voltage difference between them. And I should just say magnitude of voltage difference between them. So in this case, the shape is a sphere. Let me just shift my papers around, myself a little more space, but writing on this screen is actually kind of cool, different, but maybe I'll get better as I practice here. But then I'm not in the center of the screen, but that's okay. You guys don't need to see me. Okay, so if I were to draw a sphere, or at least a two-dimensional sphere, it would look something like this. And maybe what they're saying here is on the inner metal piece, we would build up positive charges. And on the outer metal piece, we will build up negative charges. And so again, the capacitance, which I'll circle in red here, this definition, is if you put a certain charge on here and divided it by how much voltage that created, that would be its capacitance. So its capacitance is its charge per volt. So keeping that in mind, this problem really takes us back a chapter and asks this: what would be the change in voltage? Well, maybe I'll go back to black here. What would be the change in voltage from, I'll say, A to B, where A is the radius of the inner one and B is the radius of the outer one. And so the definition of our voltage was to integrate the electric field. And so this was one of the tools back in chapter 25 that would be a good review. I know this is a question from chapter 26, but one thing neat about chapter 26 here is it makes us use the tools. I think I said in the video, if not, I'll repeat it here, that what's neat about this chapter is an applied chapter. It's actually using the capacitance. And so we have to take the science we learned in these first 3 chapters and now actually use them. And so as we start building these capacitors to really understand them, or in this case, to calculate the capacitance, we need to go back to the fundamental science. And so anyway, so that's what I'm going to do here. So maybe for the electric field, and I'll use orange lines here, you might remember this would actually go back to chapter 24, Gauss's law, that we said that the electric field coming from a charged sphere would look mathematically, at least if you're on the outside, exactly like a point. So we would get, oops, let me go back to black, an integral of negative from, say, A to B, and the electric field would be Coulomb's constant times the charge, and so this would be the charge on the inner sphere divided by the radius squared, and then of course dr. And so when you actually do this integration, I'll pull out Coulomb's constants, I'll pull out the charge, but now you have a negative, you have an integral from A to B of 1 over r squared dr. And that's, I'll just keep going in the same line, is Coulomb's constant Q. And then this is a negative of a negative 1 over r evaluated from A to B. And I'm not even going to worry about the negatives, because as I said, the capacitance really is a magnitude of the voltage difference. And so in the picture I drew up here, if I actually went from A to B, let me go into my orange again, but this line right here, A to B, if I actually went from A to B, that would be a decrease in voltage. So my equation up here is going to come out to be a negative, although I'll switch it so it becomes a positive. And so it's Coulomb's constant times Q, and I'm going to write it as 1 over A minus 1 over B. And I'll point out that I did it the long way because I thought maybe it would be helpful for you guys to actually see this integral again. But in the last chapter, you learned that the voltage from a point, and not just a point, but even a sphere, as long as you were outside, was this equation. So if you would just use this equation and put in a radius of A and then minus a radius of B, you would have got that one. So let me emphasize, you don't have to go all the way back to redoing this integral. We did it in the last chapter. You could just start here with this equation. That would be fine. All right, so now really to the heart of this problem. Let me come back over here and say, okay, and I already circled it in red once, but I'll circle it again. This is the heart of the problem right here. How do you calculate the capacitance? It's the amount of charge divided by, excuse me, divided by the amount of voltage. Okay, so coming up here, I can say, okay, capacitance is the amount of charge, so I'll put that in the numerator, divided by the voltage difference. And that's what we just did right above. So this would be Coulomb's constant times Q. And then this 1 over A minus this 1 over B. And now, of course, we can simplify it. This charge would cancel off. And we're just left with Coulomb's constant downstairs. But I noticed on the solution that they changed Coulomb's constant into the two useful constants of geometry, that's the 4 pi, and the effect of free space, that's the permeability of free space. So I'll do that. So that's the 1 over K. Then this 1 over A minus the 1 over B has a common denominator of A and B. So this would be B minus an A. And so the final step here would be to simplify that math, which in math you would call that a compound fraction. So everything that's in the denominator of the denominator gets flipped upstairs. So there's the 4 pi epsilon naught. And then there's the A, and there's the B, and then there's the B minus the A. So to actually answer part A then, I would have 4 pi, and epsilon naught is the 8.85 times 10 to the negative 12. And if we're careful with our units, that would be a Newton, a meter squared, and a Coulomb squared. And then when it comes to the radius, this is where we go back to the problem. It said the bigger radius was 14 centimeters. So I'm going to write that as points. Oh, my bad. I listed A first. So maybe I should list the smaller radius first to keep the order the same. All right, so the smaller radius was 7 centimeters. And the bigger radius is 14 centimeters. And then so downstairs, this would be the 14 centimeters, which I'll write as 0.4 meters minus the 0.07 meters. And so now I'll do the units first. I'll put it over here, but hopefully you can see that there would be a meters squared in the top, which would cancel with that. So then downstairs, if you look, there would be, maybe I'll write it in 2 steps. I'll leave the Coulomb squared, but downstairs would be a Newton times a meter, so there's a joule. And you could write this, leaving 1 Coulomb on top, and then a joule per Coulomb. And that, I'll put it down here, a joule per Coulomb is a volt. And then finally, a joule per volt is a farad. And so finally, I can say that my answer for capacitance is going to be measured in farads. Good. Let me come back to the numbers and grab my calculator. This would be a 4 times a pi times an 8.85 times 10 to the negative 12 times a 0.07 times a 0.14. Then in the bottom, I'll just do that in my head because 14 minus 7 is 7. So divided by 0.07. And so if I did all those numbers right, my calculator says 1.56 times 10 to the negative 11 farads. And maybe I'll just do one more and move the decimal 1. So this becomes 15.6. And then when I made that one bigger, that would make this one smaller. So that'd be 10 to the minus 12, and that is the prefix pico. So 15.6 pico. And just out of my own curiosity, I'm going to jump over to the solution page, 15.6 picofarads. Good. So that much I got right. And let me go back to my whiteboard here and let's keep going, because part B of this problem, so B, I wrote it down here, was, oh yeah, so what voltage would you need in order to get a charge of 4 microcoulombs? So capacitance then is charge over volts, or volts then would be charge over capacitance. So this would be 4 times 10 to the minus 6 coulombs is what the charge is. And then the capacitance that we just got above was the 15.6 picofarad. And I'll put for pico 10 to the minus 12. And for a farad, I'll put coulombs per volt, so that then the coulombs will cancel off and the volts would move upstairs when I do my compound fraction. And so good, I get an answer in volts. So now let me grab my calculator here. 4 times 10 to the negative 6, and then divided by 15.6 times 10 to the negative 12. Ooh, that's a lot of voltage. And so 256,000. And I got 410, but with 3 significant figures, I'll just put 256,000 volts, and I'll write it as a kilovolt. And in fact, I'll also switch back. What did they get? 256 kilovolts. Yay! Okay, good. It worked. And since I'm working on only one screen today, I'll turn that off for a second. I'll turn it back on for those of you. Oh, maybe I did that too quick. Did I turn it off too quick? You guys still writing?
I got it.
You got it? Okay.
Wasn't the one who asked the question, though. I'm not sure.
Oh, yeah. Okay. So, oh, it looks like Andrew asked us the question. And now that I turned off, I don't see Andrew. Am I too slow today? I'm sorry about the video camera. Is the white screen working okay though?
Yeah.
Yeah.
I kind of like it. I kind of like light on the on the white screen, but I don't know if it's quite as effective. What do you guys prefer?
Either way works for me.
Okay. All right. Well, let's see. In fact, there's quite a list here. So where was I? Number 11. Next one. Professor, are you showing your screen? It's not showing for me. Yeah. Thanks for fixing that, Max. Yeah. Okay. 122, I joined late. Okay. Max says, I have a question from 122, chapter 26, number 29. And I probably should do that. I'd like to do it and put it on video. I see Max has stepped out of the room. I saw Daniel just kind of walk away there. So Should I do this one anyways, or should I go into another question, come back?
I'd
Anybody
like
care?
to see it, but I'll be probably in your next session. So if there's someone who needs a question answered now, then.
All right, well, if anybody wants it answered now, speak up. Otherwise, I'm gonna just keep going with number 29. Sound good? And
Sounds good.
I know the rest of you might be just kind of picking up tidbits here and there and observing. That's great too. All right. So since nobody said anything, I'm going to jump into number 29 here. And to do that, I'll have to jump over to read the question. All right. So let me scroll
I'll see
down
you
here.
later. I'm gonna get some lunch.
Oh wait, I heard somebody. Was that you, Daniel?
Yeah, I said I'll see you later. I'm gonna go get some lunch.
Completely understandable. All right. All right.
Bye.
All right. Bye now. All right. So let me come back here to my question. Okay. So it was question 29. It says here, a parallel plate capacitor has a charge of Q. All right. Draw myself a picture so I'll remember this. Charge Q and plates with area A. Okay. What force acts on one plate to attract it towards the other? Okay. And it looks like then the rest of it's a bunch of hints. It says because the electric field between the plates is this, you might think of using this, which is a common mistake. This conclusion is wrong because blah, 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 blah. All right. Well, I won't worry about their hint. I think I kind of understand where the common mistake is, but I'll address that. Let me jump back over here to the Zoom and hit my share screen. Let me go to the whiteboard. All right. Oh, no. I did this one time before. That's the Zoom whiteboard. And I got more features with the Microsoft whiteboard. So let me go to the Microsoft whiteboard. Okay, let me share that one back. Okay. All right, so I'm going to assume here you guys can see the shared screen. Speak up if not. And I'll even write here. What was this? Chapter 26, number 29. And let's do a little kind of review of our parallel plates. And so if I had one plate that was charged positive, and I had another plate that was charged negative, there would be an electric field. And so I like the colors here. I can go with orange. That would go from the positive plate to the negative plate. All right, and so it goes from positive to negative. And here's the little hint that they were trying to make it clear is that back in chapter 24 with Gauss's law, we learned that the electric field between two charged plates was sigma over epsilon naught, where sigma was the charge per area. So I'll put charge over area over epsilon naught. And if we simplify that to compound fraction, we get Q over A over epsilon naught. All right, now here's the hint they're trying to say. It says, now it would be tempting to use that, but do not. And here's why. Let me take you all the way back to chapter 23. Let's say that I have charge Q1. And then over here, I have charge Q2. And the question may be, what is the force on charge number 2? And the way you calculate it is you take the charge number 2 multiplied by the field that is created from charge number 1. In other words, the field from number 1 would be Coulomb's constant times Q1 over R squared. And this is the part I want to emphasize, and this is what they're trying to show. This is the most common mistake on this problem, is that this right here, notice, is the field created only from number 1. In other words, if you're trying to find the force on number 2 here, it is the charge of number 2 multiplied by the field that's created from number 1. And so if I was drawing a field, it would look something like this. And what I want to emphasize is we do not use the field that's created by both charges when you're trying to find the force on number 2. This would take us all the way back to Physics 121 and our internal forces. You cannot push on yourself. If your car breaks down, you cannot sit in the driver's seat and push on the steering wheel and push the car forward. Because as you push on the steering wheel, which is of course forward, your back is on the seat pushing the car the other way. Those are equal and opposite forces. You can only push the car forward with external forces, not internal forces. And so that was our argument back in chapter 23, that when you go to calculate, and I'll circle it in red here, the field is the field created from the other charges. And in this case, it's just Q1. And so it's the field from Q1, then multiplied by Q2 to get the force on number 2. You never include the field that's created by itself. You cannot push on yourself. All right. So if that makes any sense, let's come back to this problem and realize that if you go back to chapter 24 in Gauss's law, and I'll highlight it again, we said this was the total electric field from both plates. What we said is that the electric field from one plate would be sigma over 2 epsilon. And the field in between them would be adding this twice. And so if you were to put a charge, and so maybe in blue here, I'll just put a charge right here. And if your question was, what is the force on a charge that's between the 2 plates, then you would want to use, and I'll circle it in blue, this field, because this is the field that's created by both plates. And then you put a blue charge between them. And so the field is the total field by both plates. But that is not what they're asking in this problem. This problem, they're asking for the force on, say, plate number 2. So what we have to do is use the field from just plate number 1. And that's why, and I'll circle it in green, I am going to use this equation for the field. And so I would write it this way down here as I get to the heart of the problem. I would say, I want to know the force, and I'll put a number 2 for plate number 2. I would take the charge on plate number 2 and multiply it by the field that's created by plate number 1. And so the charge on plate number 2 is just the Q. And the field, as I just said up there, would be the charge density over 2 epsilon naught. And the charge density would be charge over the area. And then we would have this 2 epsilon naught. And so if we go to simplify this, we would have a Q squared in the numerator. We would have a 2, and we would have an epsilon naught, and we would have the area of the plate. And had you forgotten that little warning and the hint they gave you, you would have left off that factor of 2. And like I said, certainly easy to do, but hopefully the hints did that. Now, I think that was the whole question. Yeah, good. And then let me check the solution here, number 29. Oh, okay, I see the solution. They did it a little different. They calculated the energy and took the derivative. And maybe that's better. Huh. It certainly is pretty easy, but that's not the direction I went. Well, maybe that's good. Maybe you should see both there. But we do end up with the same answer. So that's good. All right. Who asked that? Was that? Oh yeah, that was Max. And I was wondering if he came back. But I'm glad I got that on video. Andrew, did you take off here? Because yours says, does anyone know what we need to turn in for the lab? And I think you might have gotten that answer, but I'll repeat it in short form. Yeah, for the 122 lab, the big thing is really the 2 graphs. One is the capacitance versus the separational distance. That's step 6 in the lab. The other one is the capacitance versus the overlap area, which is the step 7. And then there's the minor things that I don't want to really say minor, but the other things that you want to turn in are those, I made the measurement when they were in series. You were supposed to calculate what the capacitance is, and you're supposed to then just list those right next to each other, and hopefully they'll be somewhat close to each other to convince you that the measured and the calculated do agree. And we did that for steps 1, 2, 3, 4, and then we switched. And then in step 5, you just need to write down what the capacitance is of that parallel plate capacitor. Which I measured, but you also need to calculate it and using the equation from class. And so just those things there. And then in 8, you're just supposed to take the ratio to get the dielectric constant. And then in 9, you don't do anything. You just watch me, and nothing for you to write down, but you just kind of watch me and hopefully see the light stay on for, it was quite a while, almost I think as long as a minute. And I said, just go look at the timestamp of how long the light stayed on and write that down. So I mean, I guess there is something to write down. How long did the light stay on? Okay. Let's see. Next question. I have been listening. Like, what is it? It turns out, and I'm on the wrong Zoom. Oh. All right. Oh, and then thank you, if I'm pronouncing your name right, Belikatov. You're in the correct room now. Yeah, so yeah, anybody who needs help, I think that this was face to face, there is set times, but even when it's face to face and it's set times, I just tell students, if you got a question, come on by. I'm in the lab on Friday. I'll gladly answer it. So I'm just kind of doing the same thing. Although this, I think more people come around this way outside of their class. So I like it. I hope that's not too bothersome. But I just say, yeah, everybody come and just, hey, we'll just try to answer anybody's questions who has it. The only thing I would say is that there's only 3 classes, not 4. You list, let's see, you list 102, yes, and 121, yes, or at least some of the people. Those are the people who signed up for the workshop. But anybody in 121 could come, but probably only the people in the workshop know, because they're the only ones who I have access to. I don't teach the 121 class, and I haven't got any 121 class questions today. Let's see, and then there's the 122 class. That's, yeah, a big part of you guys. And then 123 is not taught this semester, so it wouldn't be 123. So great, guys. Oh, lunch break? Yeah, I guess it is lunch break. All right. So 11, what is it, 11:38? Yeah. All right. And then, and there's nothing more down here. Okay, good. So why don't we call it a lunch break? I'll come back here at 12:30, and hopefully I'll have time to maybe get something to eat and stretch my legs, and also see if my phone's working. But I kind of liking this right on the screen. It's a little different, but I kind of like it here. Hope it's working for you guys too. But meanwhile, I'll see, stop the recording, and let's see, how do I stop? Well, it must be under more, the small screen here. Stop the recording, yeah.